AGN over cosmic time.
Thank you. Hi, so my name is Kimberly Emig, and today I'm going to talk about observing interstellar gas and galaxies in AGN over cosmic time using recombination lines at low radio frequencies. So we're just starting to make the first detections of radio recombination lines at cosmological distances. And this is something that we're going to be able to do in large populations for the first time over the next years. And with SKA and ngVLA, in the future, we're going to be able to observe this in hundreds of thousands of sources. So radio recombination lines are typically observed at high radio frequencies. And there you have the electron recombining with an atom, and the electron cascades down an energy level. And that population follows the Boltzmann distribution, and so does the line emission. But I'm not going to talk about high frequency lines today. Instead, I'm going to focus on these low frequency lines where the line emission can be significantly amplified compared with that LTE value. And so these lines are stimulated by a local radio continuum. And so you end up overpopulating certain energy levels, and that's dependent on the gas physical conditions. So this is something that occurs at 10 gigahertz or below in extragalactic sources. And in the first part of my talk, I'm going to focus on hydrogen lines coming from warm, fully ionized gas. And then in the second half, I'll focus on carbon coming from cold neutral gas. So I said that the line emission is highly dependent on the physical properties. And so here I'm showing just for each order of magnitude in density where that line emission is going to peak, or at least be half of its peak intensity. So for example, with or something else to point out is that this line emission is going to be bright over a decade in frequency. And so with ngVLA, for example, we would be most sensitive to gas with densities between 10 and 10 to the 5 electrons per centimeter cubed. And that's for a redshift 0 source, and for a redshift 3 source, then we're more sensitive to higher gas densities. And here is just what one of those, the line emission for a given density, what those models look like as a function of frequency. And so we can observe many of these recombination lines in a single observation. So for example, with ngVLA, we're going to have 53 of these lines for a redshift 0 source. For a redshift 3 source, then we just have different lines shifting into the band, but we'll still get 33 of them. And because these line properties are correlated and they're well behaved over the bandpass, we can stack many of them to increase our signal to noise significantly. And so the key science that we can do with these observations, we can study the ionized gas that either is within or along the line of sight to these radio bright galaxies in AGN. And we're really going to be limited to just the brightest sources in the sky, because the line intensity of these recombination lines is directly proportional to the continuum intensity. And so yeah, that implies that if you have a radio bright source out to a higher redshift, so redshift 2 and 3 we easily have, you can observe those lines out at that redshift. But the lines are really faint, so they only have line to continuum ratios of 10 to the minus 4, 10 to the minus 3. And just to underline that, right, for a 10 Jansky source, that means we're looking at line strengths of between 1 and 10 millijansky, and so on. But if we can detect this in a large population of sources, then we can study the diffuse ionized gas in the ISM of galaxies. So either in like absorption line systems or these intervening systems, we could potentially detect, or we do detect this in nearby galaxies. These nearby radio bright galaxies, and then we could potentially detect this in the host galaxies of AGN. And so the key strength of this is that this is going to be a dust unobscured view and a metallicity independent probe of the physical properties of that gas. So it's highly complementary to other traces of ionized gas that we have at shorter wavelengths, but it can provide a really key comparison. And in AGN, if we can detect this in the AGN, we can learn about potentially these narrow line regions, gas in the circumnuclear disk, particularly for compact and peak spectrum AGN, we can get a handle of the ionized gas or the free gas that's there, and that might be affecting the SED of these sources. It seems like the Lyman alpha halos can have a high enough density also that we can potentially detect this there. And with the kinematics, we can also get, is this ionized, we can get a handle on the gas kinematics as well. And I'll just draw your attention to this study by Menti et al., who made these SKA predictions for obscured quasars. So the state of the field, there's in the early 70s and 80s, so like about 30 galaxies, distant galaxies in AGN were searched, and there was this one detection at a distance of 340 megaparsecs, but it took 40 hours to detect these two recombination lines. So with the telescopes, like their sensitivity and the instrumentation that we had at the time, just it really wasn't feasible. But so now we have 24 galaxies detected in recombination lines. Most of that has been, most of these galaxies have been observed at higher frequencies, but still 9 of them show this evidence for stimulated recombination lines. And then we're now just making these first detections outside of the local universe. And so, yeah, I'll tell you more about this observation that we did with the Meerkat absorption line survey, where we observed PKS 1830 minus 2.1, just as the first source to verify the system performance. And so this source is actually a radio blazar at a redshift of 2.5, and it's being strongly lensed by a galaxy at a redshift of 0.89. And we detect the recombination lines intrinsic to that 0.89 galaxy. And there on the top right, you can see how that recombination line emission compares to the H1 and the OH that we detect in the system. So we also see these lines in the lower frequency UHF band. And with just these two frequency measurements, we can compare the line intensities to models and try to infer some physical properties. So you can see the emission measure constraints there. And the key thing is that we can disentangle that density from the emission measure. And with just our models observations alone, we're able to get a handle on the star formation rate, the ionized gas from the recombination lines. We also had the H1 and the OH detection to characterize the cold gas. So I thought that's really interesting, something that you can do with just these survey observations. And yeah, so it seems like this galaxy can have a star formation rate of around 50 solar masses per year, and yeah, 10 to the 11 solar mass. And so now it's really thanks to these wideband large area H1 surveys that we're going to be able to do these large population studies over the next years. And so here I'm showing some of those surveys, their frequency coverage, the number of lines, and then the effective RRL stacked noise, assuming 70% of those lines. You see the sky coverage. And then the number of sources that we'll be able to look in with a line to continuum ratio of 10 to the minus 3 at a 3 sigma level. So we'll be able to make these really interesting searches in thousands of objects for the first time, and really just make the first characterization of like a detection rate, figure out what kind of science and we can do in the environments that we're going to be able to detect this in. And so when we think about the future, then the impact of the SKA is really thanks to these precursors that we can make these large population studies. And I think a key strength is going to be the low frequency coverage that we have, which is going to give us sensitivity to those high redshift sources. It's going to provide a key multi-frequency data point there, so we can derive the physical conditions of the gas, and it's going to be sensitive to lower gas densities. And so if we would take this MILES survey, which we observed in L band for 60 minutes, UHF band for 90 minutes. If we could do that with SKA, then we can have a factor of 4 increase in the sensitivity. That gives us, more than 10,000 sources now we can look at. And if we could do this over 30,000 square degrees, then we can do this in more than 100,000 sources. And so this could be a really great complement. If DSA 2000 comes to fruition, that could cover the northern hemisphere, and this would be a really great southern hemisphere complement. And so for ngVLA, I think it will be the key strengths there are going to be following up these detections that we make and doing these studies at high resolution. So being able to do spatially resolved analyses when you have sort of narrower line widths with fewer Doppler components, then you can potentially detect helium, recombination lines, and look at the ionization state of the gas. And at those higher frequencies, then we're going to be, we can probe higher gas densities, and again, provide a really crucial measurement for multi-frequency. Okay, so in the last 5 minutes now, I'm going to focus on carbon recombination lines. So these, so carbon can be ionized in gas where hydrogen no longer is. And these carbon recombination lines are really weighted just towards that cold gas. So they end up tracing this cold H1 and CO dark molecular gas. And they're really become really bright at frequencies below 500 megahertz. And so as an example, I wanted to just take this spectrum in our galaxy. This is a spatially average spectrum over 150 parsec by 150 parsec region. This is a higher frequency observations, typical recombination lines in LTE. You see where hydrogen is. You see carbon is offset by 150 kilometers per second. And as we go to lower frequencies, these lines are getting much brighter because the radio continuum is getting much brighter and they're stimulated. And you also see how the carbon line is getting brighter with respect to hydrogen. So that as we go to lower frequencies, then carbon is going to be the brightest emitter there. And this is a really interesting way that we can isolate this phase of cold H1 and CO dark gas. It's notoriously difficult to do. And this can give us a really key way to learn about how molecular clouds form. So using these multi-frequency line analysis, we can derive physical conditions of this gas phase, really look at this H1 to H2 transition. So we can measure formation rates of molecular clouds. We'll infer the kinematics and measure the gas pressures. And these are all really key things in models and simulations of molecular cloud formation and galaxy evolution. So these lines are also highly complementary to C+ observations, the C+ at 158 micron, and especially when we think about these H1 absorption, higher redshift observations, this is really complementary to that. So we had observed 3C190, which is a radio quasar at a redshift of 1.19. So you can see it's in this really complex environment undergoing minor and major mergers. We observed this with low fire at 134 megahertz. And we detected this recombination line, which we think is most likely coming from carbon, has quite a narrow line width, and yeah, coming from some foreground emission to 3C190. So this was the first recombination line detection that sort of broke that redshift barrier and really showed that these high redshift studies are feasible. And so now when we think about the future of the field and the impact of SKA, we have these lessons learned from LOFAR that when we take these really nice wide bandwidth observations, we had to make sure that the subbands are wide enough to be sensitive to these extragalactic recombination lines. So we need the flexibility there. Another thing to point out is that these surveys that I mentioned, they can provide key constraints also for these carbon recombination line observations. And even these surveys that push down to lower frequencies can potentially detect carbon lines for the most nearby sources. And if you're designing a 400 to 800 megahertz experiment, this is a really great science to keep in mind for that. And SKA low can really completely revolutionize our view of cold neutral gas using these carbon recombination line observations. So it'd be really great to do a survey with SKA low, a spectral line survey with SKA low. So in conclusion, these stimulated recombination lines are observable outside of the local universe, yay. Deep wideband large area spectral line surveys are opening up a new discovery space for these recombination lines. And I told you about hydrogen. They're dust unobscured metallicity independent tracer of the ionized gas and kinematics. And these carbon recombination lines can really be useful probes to learn about molecular cloud formation. So thanks for your attention.
Nice talk, Kimberly.
Thank you.
Would you care to speculate about recombination lines forming a spectral line foreground for epic reionization experiments?
I don't care to speculate. Yeah, I mean, yeah, so that's something that, well, within the galaxy, I think there's still so much that we can do in the galaxy, still so much that we don't know about even this low frequency carbon line emission. So yeah, SKA is going to be really great also for galactic studies. That's something, you know, really key that I think we still need to understand. And then I think also just, you know, if you have this spectral line, all these recombination lines, even in extragalactic sources, if you're trying to like subtract them or remove them, yeah, that's something to keep in mind, that you can have this signal. So yeah, more to investigate there.
There's a question up there.
Yeah, thanks. Sort of, could you remind me what column density of gas you need to be sensitive to, and like for example, like how far off, what impact parameter can you detect? Like how far away does the quasar can be from like the center of a galaxy to detect these lines?
Yeah, so let's see. We don't have many examples, right? We only have just a few. That one example I showed you, it was PKS 1830 was being strongly lensed by the system, and so the radio core images were passing through just like a radius of 5 kiloparsecs from the galaxy. But there, then that gas ended up being like quite high in density. Whereas we go to larger galactic radii, maybe we have gas of lower density, larger filling factors though. And yeah, so that would be something that we will need to explore. But yeah, it's this emission measure, not necessarily like column density, that's the key observable that's dictating that line intensity.
Sure.
Yeah, thanks. Nice talk. So instead of using redshift surveys and continuum surveys to do science like this, have you thought about the possibility of just blind redshift surveys from recombination lines obviously with the VLA, with the ngVLA or the SK?
Yeah, so I think that's something really interesting. In like a 2020 paper, I had also developed this method, right, to search blindly in redshift space for the recombination lines, because you know that the frequency spacing between each line is unique, right? So if you can detect the lines, you know the redshift. And I think that that's something really interesting to explore. You know, potentially we can detect ionized gas where we might not always detect like H1 absorption, for example. But the lines are very faint, so yeah, something definitely to try out. And
so how much does the non-LTE nature affect the ability to stack? So if you can't count on the line ratios depending on frequency as you normally expect, does that make it difficult to stack at low frequencies?
Well, because the line intensity, it's only changing on sort of like a decade in frequency sort of space, right? So like the bandwidths that we're observing are like relatively narrow. So yeah, you don't expect the line intensity to change that much, that the stacking is reliable.
So you're okay for an octave or two, but
yeah. That's general.
So I have one question. The numbers that you gave in your table, did that account for lines that you might lose to RFI?
So I just assumed that like 70% of them would be available, and that's just, you know, some fraction that I chose, but that's not. Yeah, I guess that's yeah, that is for the Meerkat observations. I think that's what it was, around 70% or 60%. Yeah, but nothing more detailed than.
Okay, I think we should move on. So let's thank our speaker.
Thank you.